Dear students, now we discuss 2 by 2 autonomous system of differential equations. This is generalization of second order ODEs we discussed earlier. Here also we find characteristic equation and provide general solution depending on various cases of solutions of characteristic equations. So we consider system of the form dx by dt equal to a1x plus b1y and dy by dt equal to a2x plus b2y, where a1, b1, a2 and b2 are constant. Okay, so we have simultaneous equations. This system is called autonomous because the independent variable t is absent in this system. I mean, it is not present explicitly in this system. So these are equivalent to second order linear homogeneous differential equations. Okay, so for non-homogeneous equations, we have some function of t which is appearing in the system. Here a1, b1, a2 and b2 are constants, so t appears only in x and y, so it is not present explicitly. This system 1 is equivalent to vector equation dx by dt dy by dt equal to matrix a1, b1, a2, b2, xy. Okay, so we can check easily. So if we take matrix multiplication on right side, we get a1x plus b1y as the first entry, and so we have dx by dt equal to a1x plus b1y. Okay, it is same as system 1. Similarly, dy by dt is a2x plus b2y. The characteristic equation of coefficient matrix in system 2 is m square minus sum of diagonal entries. into m plus determinant of coefficient matrix equal to 0. That means m square minus sum of diagonal entries. It is also called as a trace of matrix. Okay, so here trace is a1 plus b2. These are diagonal entries. Okay, so sum is called as trace. And determinant is a1 b2 minus a2 b1 equal to 0 in variable m. Okay, so this is quadratic polynomial in variable m. So if we solve this, then we get two values of m, maybe distinct real or repeated real or complex conjugate values. And using these values, we can provide general solution of this system. So next important step is the general solution. Okay, so we try to find solution of the form x equal to a e raised to m t y equal to b e raised to mt. Here a and b are constants to be determined and m will be root of characteristic equation. Since we want solution in this form, we substitute the values of x and y in 3 in given equation 1. Substituting values 3 in system 1, we get, so left hand side of 1 is dx by dt. Okay, so here a and m are constants, so we have m into a e raised to mt, okay, dx by dt equal to a1x, so a1 into a e raised to mt plus b1y, b1y is b raised to mt, and second equation is dy by dt. dy by dt is m b e raised to mt. Okay, so y is b e raised to mt. Differentiation is m into b e raised to mt equal to right hand side is a to x. So a to a e raised to mt plus b to y, that is b e raised to mt. Now we can divide this system by e raised to mt. E raised to m into t cannot be 0. Okay, so we can dividing by e raised to mt and simplifying, we get, so it is m minus a1 into capital A. Instead we take this to right side, so we write a1 minus capital A. We take this to right side, a1 minus m into capital A plus b1 into capital B equal to 0. First equation. Second equation is a2 a plus b2 minus m into b equal to 0. Okay. This is system in capital A and capital B. Okay. So this is a linear system of equations in capital A, capital B. This has trivial solution. Capital A equal to 0, B equal to 0. Okay. But we don't want trivial solution. So non-trivial solution exists if determinant of coefficients is 0. So let us see. This system has trivial solution A equal to B equal to 0. This gives, okay, so if we substitute these values in 3, A equal to B equal to 0, then we get X equal to 0 and Y equal to 0. So X equal to Y equal to 0 as solution of 1. Okay. So differential equation 1 has this solution X equal to 0, Y equal to 0. This is called equilibrium solution. Of course, we want solution which is not 0 always. Okay, so for that we need non-zero values or non-trivial values of capital A and capital B. To find non-trivial solution, we must equate the determinant of coefficients in this system 4 to 0. determinant of coefficients is that matrix is A1 minus M, B1, A2, B2 minus M. Okay, so this M should be small letter. So we must have determinant of A1 minus M, B1, A2, B2 minus M equal to 0. That is A1 minus M, B2 minus M minus A2 B1 equal to 0, and this is M square minus A1 plus B2 M plus A1 B2 minus A2 B1 equal to 0. Okay, so this is characteristic equation of matrix, coefficient matrix we already have seen. Okay, so A1 plus B2 is trace, and this is determinant of coefficient matrix. Okay. So this is characteristic equation. This is quadratic equation, so it will have two roots, maybe equal roots. So we call them as M1 and M2. Let M1 and M2 be the roots of phi. So once we get these values, we replace this M in 3 by M1 and then M2, and then we get values of values A and B, capital A and B, using this 4. Okay, in 4, if we substitute value of M as M1, then we get values of A and B. Substituting M equal to M1 in this 4, system 4, we get non-trivial values. A1 and B1. Remember that there are two equations in system 4, but these two equations will produce single equation because we are substituting this determinant to be 0, determinant of coefficient to be 0. So the two rows in this matrix. Okay, so the first row and second row, these are constant multiples of each other. So we will get single equation from these two equations in 4. Anyways, so we will have infinitely many values for A and B, and we can take any one such pair A and B which is non-trivial. That means where we get non-zero values of A and B. Okay, so this gives one solution. Therefore, x equal to a1 e raised to m1t, y equal to b1 e raised to m1t. This is one solution, non-trivial solution of system 1. Similarly, we replace m by m2 in 4 and we get values a2 and b. Replacing m by m2 in 4, we get non-trivial values a2 and b2, and therefore x equal to a2 e raised to m2t and y equal to b2 e raised to m2t is another non-trivial solution. Okay. Of course, these two are different solutions when m1 is different from m2. So, general solution. First case is real distinct roots. So, first case is m1 and m2 are real and distinct. Then these two are independent solutions. So we may call this as, I think it is 6. Yes. And this one 7. So these two are independent solutions. If m1 and m2 are real and distinct, then 6 and 7 are linearly independent. Okay, it can be said easily. Linearly independent solutions of system 1, and therefore general solution is x equal to c1 a1 e raised to m1t plus c2 into a2 e raised to m2t, and y is given by c1 b1 e raised to m1t plus c2 b2 e raised to m2t, where c1 and C2 are arbitrary constants. Okay, so this is general solution in case of real distinct roots. In the next lecture, we discuss complex roots and repeated roots. Thank you.